have this AC source. Um, and we're connecting various circuit elements. We start off by connecting a capacitor, then an inductor, and a resistor. So this is the black box we're connecting the AC source to. All right. The average power output, you guys can see is VRMS times IRMS times the power factor, cosine phi. Okay? And phi is given by tan inverse of XL minus XC divided by the resistor. Yeah. So if there is a resistor. But, all right, so here's the power factor. For part A, when you connect a capacitor, for a capacitor, phi is it minus pi by 2. Okay, and cosine phi will be 0. And power is 0. All right, so what this equation is saying, the average power delivered to the capacitor is 0. What happens is the energy is delivered to capacitor in one cycle, and then that energy is delivered back to the source. Okay. So again, if you have a purely capacitive circuit, no power is delivered to the load. For part B, when you connect an inductor, phi is pi by 2. Average, again, cosine phi is 0. Average power is 0. Okay, no power is delivered to inductor. Same thing as capacitor. Energy is delivered there in half a cycle, and then that energy comes back, right back. Only for a resistor, so phi is 0. So average power delivered is VRMS times IRMS times cosine phi, which is 1. Okay, so VRMS is Vmax by root 2, Imax over root 2 times 1. 100 volts divided by root 2. See, Vmax was 100 volts, and Imax will be Vmax 100 volts divided by 50 ohms divided by root 2. Okay, so this is 10,000 divided by 2 is 5,000. 5,000 divided by 50 is 100. So the average power delivered to the resistor is 100 watts. Okay. So this is like a 100-watt bulb. So this problem says an AC source of voltage amplitude 10 volt delivers electrical energy at the rate of 0.8 watts when its current output is 2.5 amps. What is the phase angle between the EMF and the current? Okay, so amplitude of 10 volts, that's the power. So the power delivered you saw is Vrms times Irms times cosine phi. This is the power factor, and that's the phase angle between the current and the voltage. Okay, so just to remind you guys, so this is where that shows up. That's where that angle shows up. Okay. All right, so when its current output is okay, so cosine phi is P average over Vrms over Irms. And these are maximum values. That's Vmax, and this is Imax. Okay. So RMS values are Vmax over root 2, Imax over root 2, so you get 2 over here, and that 2 comes over to the top. So 2 times 0.8 watts divided by 10 volts times 2.5 amps. And volts times amp is watts, and that watts cancels with that. So this is a dimensionless number, cosine phi, so 1.6 over 25. So, and this comes out to 86.3 degrees. And if we want to convert this to radians, .5 radians. Okay. So it turns out it's an inductive circuit. So this problem says the resonant frequency of an RLC series circuit is 2000 hertz. If the self-inductance in the circuit is 5 millihenry, what is the capacitance in the circuit? Okay. So the resonant frequency is they give you the resonant frequency and they give you the inductor, so we can calculate the capacitance. Okay. So F is the linear frequency is what they have given. Okay, that is killed by one of those, so that's 4,000. and into 5, and this will come out in farads. Okay. This 10 to the power of, oops, we'll bring this 10 to the power of 3 to the top, and this becomes 16 pi square times 5. Okay, so the capacitance is 1.27 microfarads. Okay. Okay, this problem says, what is the resonant frequency of a resistor, capacitor, and inductor connected in series? So you have connected RLC circuit. So this is connected to a 100 volt source operating at resonant frequency. Okay, so, and we'll assume that's the amplitude of the source, where omega is 1 over root of LC. Okay. So at resonant frequency, at this frequency, see, phi is tan inverse of XL minus XC divided by R. At resonant frequency, this is equal to that, so phi is 0. At resonant frequency, phi is 0. Okay, so we'll find out the resonant frequency. Omega is L is 2 henries, C is 5 microfarads, so square root of that is 10 minus 3, that comes to the top, so that's 10 to the 3 over root of 10 radians per second. Okay, so that's the resonant frequency, 316 radians per second. Okay. And now, if this combination is connected to a source, what is the power output of the source? So the power output, again, the average power output is VRMS, IRMS, cosine phi. And at resonance, phi is 0, so this is 1. And VRMS is Vmax over root 2, and IRMS is Vmax over Z times root 2. This is Vmax times divided by Z is Imax. Imax divided by root 2 is IRMS. Okay. Z in our case is just R square plus XL minus XC square. And at resonance, this is 0, so Z is equal to R. Okay. So the average power delivered is Vmax square two times R. And this is 100 volts source divided by 2 times 100 volts, and resistance is 100 ohms. Okay. So that's 50 watts. And what does part C say? What is the Q of the circuit? Okay. So let me show you, remind you what Q is. Okay. So here's the circuit, here's the load, and as you change the frequency, the power delivered to the load changes, and that's what this is showing you. So the power delivered, average power delivered to the circuit as a function of frequency is shown like that. And at resonant frequency, that's when the maximum power is delivered. Okay. See, at lower frequencies, less power is delivered, and at higher frequency, less power is delivered. Okay, so what they're asking is the following. What is the Q of the circuit? The Q of the circuit is, this is the quality factor of the circuit is, it's the resonant frequency divided by the width, okay? And narrower the width, sharper the peak, and the better the tuner it is, okay? So that's the quality factor. And so the quality factor is omega naught L over R. So the quality factor of the circuit and we just found omega naught. Omega naught is the resonant frequency, which is that. L, what is L for the circuit? 2 henries, and resistances 100 ohms. So the quality factor is about 6. And the quality factor, see, it's a frequency divided by a frequency, so it's a dimensionless number. Okay. And then D, the bandwidth of the circuit. Okay, so we found the quality factor. We know the resonance, and we can calculate the bandwidth. The bandwidth is really R over L, but So the bandwidth tells you, okay, so the resonant frequency was 312 hertz. How far do you have to go before the power delivered is half its maximum value? All right, so the bandwidth tells you that. So delta omega is 316.2 radians per second divided by 6.32. Okay, 50 radians per second. Okay, so that's the width. That is the width of that. So that means you go 25 radians per second on this side or 25 radians per second on this side. The power delivered is half the maximum. Okay, so let's write that down. So the frequency range is, well, so 316.2 plus or minus 25. So 25 is 316, 390, no, 15, 10, 390. Okay, so in this frequency range, you'll catch a good signal on this tuner, or a good amount of power is delivered to the circuit. Okay? That's what that width tells you.
For part A on that one,
Mm-hmm.
it asked for the resonant frequency, but we did the angular frequency. Is it the same thing, or do we need to use the effective?
Yeah, resonant frequency just resonant frequency just means when is the power delivered when is maximum power delivered. So IRMS is maximum when this is 0. And that's 0 at that frequency.
So we do not need to use the 2πf is equal to the angular frequency for that one to break it down into frequency.
Yeah, I mean, where there we just stated in radians per second. If you want to convert,
Okay.
if you want to convert that to linear frequency, just divide that by 2 pi.
So we did use that extra. Okay. Let me get on
All
there.
right. So this problem says a step-up transformer is designed so that the output of its secondary windings is 2000 volts. So you guys remember a transformer. This is the primary windings and this is the secondary windings. And it says, so these are RMS voltages. Is connected to a 110 volts input line. So if there are 100 turns in the primary windings, how many turns are there in the secondary windings? Okay, so this is a step-up transformer. So this, okay, and the relationship is V2, the output voltage, is N2 minus N1 times V1. And if you put RMS voltage here, you get RMS voltage here. If you put maximum voltage here, you get maximum voltage. Okay, so N2 is N1 V2 over V1. There's 100 turns in the primary, 2000 volts divided by 110 volts. So N2 is 1800 turns. Okay. That's part A. And then part B says, if a resistor connected across the secondary windings draws an RMS current of 0.75 amps, so IRMS. So power output is VRMS times IRMS. What is the current in the primary winding? Okay. Now again, like we've said, there's no free lunches. Input power is equal to output power, or output power is equal to input power. So input power is VRMS, IRMS. Let me write it in two steps. Input power is equal to output power. So VRMS, IRMS, input equal to same thing, output. Okay. So we have 110 volts input and 2000 volts output. So 110 volts times input equal to 2000 volts times output was 0.75 amperes. So input current is input RMS current, that is 13.6 amps. So this transformer steps up the voltage and steps down the current. The current went down from 13.6 amp to 0.75 amps, and voltage went up from 110 volts to 2000 volts. Okay. All right, one last problem. This says a transformer is used to supply a 12-volt model train with a power from a 110-volt wall plug. And that's an RMS voltage. The peak voltage coming out of the wall is 170 volts. Okay. The train operates at 50 watts of power. Okay. So the output power is 50 watts. What is the RMS current in the secondary coil of the transformer? Okay. So part A, we'll write V, and these are all value, RMS value input is V out over I out. So we are given V out, we are given V in, and we know this is power out. This is given, so I out is given. What is the RMS value of the current? So this value, I input RMS, is just V out, I out, and these are all RMS values. V in. Okay, and so this works out to 50 watts divided by 110 volts. And 0.45 amps. So the input RMS current is 0.45 amps. And then part B, what is the RMS current in the prime? Oh, what is the RMS current in the primary coil? That's what we found. So we'll call this B. And A is, what is the RMS current in the secondary coil? The secondary coil, the RMS current, they give you power 50 watts. So the current in the secondary coil is power divided by the output voltage, which is, so 50 watts divided by the output voltage is 12 watts. .17 amps. That was the output current. Okay, so this is part A, B, then C. What is the ratio of the number of primary to secondary turns? V in, no, V out equal to N2 over N1, V in. N2 over N1 equal to V in over V out. And no, V out over V in. Output voltage was 12 volts, input voltage was 100. Okay, so what this says is for every 10 turns in the primary coil, there's 1 turn in the secondary coil. Okay. So remember, this is a step-down transformer. So essentially, for 110 volts, you're getting 1/10 the voltage, output voltage. So the number of turns is 1/10 the number of turns. So what is it? And what is the resistance of the train? What was this? Let's see. So power output is V out, I out. And so the resistance of the train is square divided by P out. And that was 12 volts square divided by 50 watts. Okay, roughly 3 ohms. .88 ohms. Yep. And then what is the resistance seen by the 110 volt source? So the input resistance. Okay, P in equal to P out, V in square divided by. Input voltage was 110 volts square, and output power was that. Okay, so the resistance seen by the input circuit is 242 ohms. All right, so that finishes the problems from this chapter.